As we begin our new probability standard, let's go back to a vocabulary term I first introduced in the intro lesson, which is probability distribution, or specifically a probability distribution table. And that's what I have right here. I have a probability distribution table. It's specifically for rolling one standard six-sided die. And what you're going to see is I've basically listed the entire sample space, or all possible outcomes or events. And all these outcomes are also mutually exclusive, and therefore you can't overlap them. And then what I'm going to see underneath them is I'm going to see the probability of each of those events, and those are the theoretical probabilities specifically. And since it's 1/6 of the time I'll roll a 1, 1/6 of the time I'll roll a 2, and so on. And I just keep doing that and list it all out. Now when I'm done, I better have exhausted the whole sample space, meaning I better take 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 and get the sum, there's our sigma notation, of all the probabilities. That's why it goes from 1 to n being all the number of ways that you could roll, in this case 6, and I better add up to 1. Again, 1 means that, probability 1 means that it's guaranteed to happen. So as you make your probability distribution table, make sure there's no overlapping events, and make sure that all your probabilities are valid. Now I know it says it falls between 0 and 1, but I'm not going to list all the events that are 0. There's way too many of those. I mean, think about this. If I roll a 1 standard six-sided die, I could say, what's the probability of rolling an A? It's not going to happen on a standard six-sided die. So why would I put the 0 there? Because then I could do that for a lot of letters. And if I had actually one event that had a probability of 1, because that's all you could have, because anything else would be greater than 1, and that doesn't make sense, then it would just literally be one item. So when I say probabilities are valid, I'm usually going to find numbers that fall between 0 and 1, but not actually 0 and 1. But mathematically, you could do it, I guess. And what I'm looking for is called the expected value, or the expected mean. Means, theoretically, if I was to keep doing this, one event, roll a die, roll a die, roll a die, roll a die, and I wrote down all the events, what would be the average value that I would actually get? And for that, we call this mu. This is the Greek letter mu, and we're going to say that this is equal to the sum, there's your sigma notation, of you taking your event numerical value, which in this case is the 1, and multiplying it by the probability of that event, 1/6. So the math of this event right here is actually the work right there, 1 times 1/6. And then what you do is you add it to the event of rolling 2 times 1/6, and so that would be this event. And then you add that to 3 being multiplied by 1/6, and 4 being rolled by 1/6, and 5 being rolled by 1/6, and finally take 6, happening 1/6 of the time, so you say 6 times 1/6. And when you add up those results, you get 21/6, and so I'm expecting the average value of a dice roll to be 3.5. And let's just look at it from a different perspective, and you're going to still see the same math, but it's going to be written a little differently. Like if I actually rolled a dice 6 times, and I had a 1, and I actually rolled a 2, and a 3, and a 4, and a 5, and a 6, I would get a sum of 21, and there's the 21. Well, the 1, 1, 1, 1, 1 is like saying, well, I rolled it 1 time here, and I rolled it 1 time here, and I rolled it 1 time here, and 1 time here, and 1 time here, and 1 time here. And then you have to remember that I was adding those up all that time, and then in the end, I still needed to take this result and divide by the number of times I actually rolled, which in this case is 6, and I get 3.5. I mean, the math is identical. It's just kind of how you come across or present it. Well, what I actually did is I did this with random.org. The only difference is I just rolled it 5 times. And the reason I did it 5 times is I don't always expect what actually happens to be what theoretically should happen. And if you set up a situation where literally you, let's say, only roll 1 die, there's no way it's going to ever land on 3.5 because it's only going to be an integer number from 1 to 6. So I chose to roll 5 numbers, and you'll see here that it went 6, 1, 5, 2, 5. So I'm going to write that over here. I won't. Okay, so what actually happened was 6, 1, 2, 5, 5. I think I may have gotten them in the wrong order. Let's take a peek. Yeah, 6, 1, 5, 2, 5. I just put these in the wrong spot. It's not going to affect anything, but just in case someone wants to emphasize that. There you go. And so if I added those up, 5 and 5 is 10, and then 6 plus 1 plus 2 is 19. In this case, I had 19. If I take 19 divided by 5, my average, represented by that symbol, works out to be 3.8. Okay, so it wasn't that far off from 3.5, which is what I theoretically was expecting. This is what actually happened. Well, as we continue on doing more and more dice rolls, I would expect, if this is truly a random die that meets these criteria, that the answer would get to closer and closer to 3.5. And so I did this again with random.org, except this time I had to do 60 rolls. And there you go, there's your 60 rolls. And I entered that into a spreadsheet. And here's the spreadsheet with those numbers, and you'll see that after 60 rolls, I was getting an average of 3.48333. So it is very close to my expected value. And then I did, ahead of time, before I even presented this lesson, I chose to do 100,000 rolls, similar to what I did in the probability intro lesson. I found the average to be 3.4967, and after a million rolls, I found it to be 3.4972. So I think we're pretty darn close to our expected value. If I was doing the rolling the sum of two standard six-sided dice, I would have sums from 2 to 12. We've learned that there's only one way of getting a 36, so I would take the 2 times the 136, and I would add it to the fact that there are two rolls, a 1, 2, and a 2, 1, out of 36. They give me a 3, so I would add that. And I would keep going 4 times the 336, plus 5 times the 436, 6 times the 536, and so on. Remember, 7 is the most likely sum you'll get off two dice, 6 out of 36. And then it'll continue on, and you'll find out that you could have a sum of 252 over 36, which works out to be exactly 7. Now, this doesn't surprise me because a standard die has a expected value of 3.5, so therefore if I had two standard die, each one having an expected average of 3.5, then I would have an expected average or expected mean of 7, 3.5 times 2. And I, again, simulated this with 100,000 rolls, and I simulated this with 1 million rolls, and you'll see that I am extremely close to my 7. Here I'm slightly over, here I'm slightly lower than that, but in either case, I am very close to my expected value of 7. So what we're going to do is we're going to look at this particular die. We're going to write out sample space, and this is the same die we came up with when we had done this in the intro lesson. So we had 1, we had 3, and we had 6. There really is no reason to write the 2 or the 4 or the 5. I know that 1 occurs 3 out of 6 times. I know that 3 occurs 2 out of 6 times, and I know that 6 occurs 1 out of 6 times. All right? Now, before I go any further, I just want to make sure that, yes, all probabilities are valid. So that's good because they're all between 0 and 1. And I know that if I take 3, 6 plus 2, 6 plus 1, 6, all right, first they don't overlap, so they're mutually exclusive, so let's make sure we do that. But if I add those up, I get 6, 6, which is 1, which is also checked. So everything's working out. I have a valid probability distribution table, so if I'm trying to figure out what the average dice roll of this is, I'd be going 1 times 3, 6. I'd be going 3 times 2, 6. And I'd be going 6 times 1, 6. And this ended up working out to be exactly 2.5. Our last question, specifically in regards to just learning how to do the expected value. We're going to keep doing expected values, but we're going to make it a little bit more elaborate. It says you buy a $5 raffle ticket. If you have 1,000 tickets that are sold, and there are 10 third-place winners of $25, 3 second-place winners of $100, and 1 grand prize winner of $2,000, construct a probability distribution table. Now remember, if you actually have a losing ticket, that ticket was worth minus $5 because you spent $5 on that ticket. Which means if you actually had a $25 prize, you would have won $20. If you had a $100 prize, you're actually a $95 winner. And if you're actually a $2,000 winner, it's really because you won $1,995 once you subtract the $5 cost. Well, we know that there's only 1 out of 1,000 tickets that will win that prize. Just like we can see that there are 3 out of 1,000 winners. And the third place winners of $25, there will be 10 of those out of 1,000. So what I still need to do is figure out what the probability of this particular value is. This would be an excellent situation for a not, okay? So if I'm trying to figure out what the probability of winning -5 is, maybe it'd be better off to thinking is what 1 minus the probability of not having -5. And I would just simply go, okay, I have 1 minus, and then I could take my 10 1,000ths, and my 3 1,000ths, and my 1 1,000th, and I would realize that that works out to be 986 1,000ths. And so that's what's going to go right there, 986 1,000ths. And so if I'm trying to find what is the average ticket value's worth, I'm going to have to take -5 and multiply that by 986 over 1,000. I'm going to add 20 times 10 1,000ths. I'm going to have to go 95 times 3 1,000ths. And then finally I'm going to have plus 1995 times 1 1,000th. And when I put that into the calculator, I found out that that was the same as -2,450 over 1,000. So the average ticket value's worth was -$2.45, or $2.45 of profit for each ticket. That went, of course, maybe to a, let's say, a charity. And if you have 1,000 tickets like that, that means they know that they should be making $2,450 worth of money, and knowing because they'll have given away $2,000 and $300 and $250. But after those prizes are gone, everything else is theirs to earn. And that's how that particular system works.